Often reported as 846 airframes, the FW-189 was a rare machine even before the wreck was found. Today, only one substantially complete example is known to survive. The survival of Werknummer 2100 was not the result of a perfect seal from history, but of decades of extreme isolation after the crash. The aircraft went down in the Karelian forest south of Murmansk, where even a reported early discovery did not lead to serious recovery for nearly half a century. In 1991, the objective was procedural: confirm the wreckage, establish a structural baseline, and secure the airframe before the last major physical evidence of the program was lost. The recovery operation began with a fundamental constraint boundary. The target was highly specialized and lightly built. It was not designed to withstand decades of exposure to extreme weather. The Karelian forest sits on the fringe of the Arctic Circle. The region is defined by deep winter snow, freezing temperatures, and zero infrastructure. For 48 years, the wreckage was subjected to continuous seasonal cycles. Snow loading deposited heavy weight on the fragile duralumin structures every winter. Spring thaws introduced moisture, and subsequent freezes caused ice expansion within every structural joint. Despite these relentless mechanical loads, the airframe maintained its physical integrity. When recovery surveyors reached the site in 1991, they found limited post-crash disturbance, including reported removal of some equipment, but no industrial development had reshaped the terrain. Every observation on the forest floor had to be sorted against a strict known and unknown boundary. Coordinates and type identification were known. The internal condition of metal, weakened by nearly 5 decades outside, was not. The surveyors therefore treated the site as a fragile evidence repository, where moving even a single piece of debris without a plan could compromise the assembly. The baseline assessment required detailed mapping of the surviving components. The FW-189 was characterized by its extensive greenhouse canopy and twin tail booms. These features made it an exceptional observation platform, while leaving many exposed surfaces vulnerable to damage under external loads. The surveyors noted that the central crew nacelle was largely composed of thin metal framing and plexiglass. It was not a heavy armored shell. The survival of this specific structure after decades of snow, cold, and forest pressure was remarkable, even for an aircraft type remembered as tougher than its appearance suggested. The 48-year gap created a specific forensic environment. The thick timber surrounding the wreckage acted as a windshield and kept the airframe from shifting. That static position prevented the grinding friction that typically destroys aircraft resting in more exposed locations. The discovery of Werknummer 2100 forced a massive operational shift from theoretical search to active preservation. Identify which surviving structures could be handled without collapsing the evidence already mapped. The ground assessment confirmed a narrow recovery window. The airframe was intact enough to justify extraction, but vulnerable enough to make every handling decision dangerous. The operation now faced a distinct physical puzzle: how a fragile, heavily glazed observation platform had survived a forest impact intact. On May 4, 1943, the aircraft operated at an altitude of 20,000 feet. 31 minutes into the mission, a severe operational threat emerged when Soviet Hawker Hurricanes engaged the reconnaissance platform. The pilot had only one escape geometry: descend hard, trade altitude for airspeed, and break the interception angle before the forest closed beneath him. The aircraft carried a crew of 3. That descent left only a narrow pull-out window before terrain intersection. The pilot could not complete the recovery arc within the available altitude. The aircraft clipped the uppermost branches of the dense timber, initiating an irreversible alteration of the flight path. Forward kinetic energy met immediate, progressive resistance from the rigid forest canopy. The evasive maneuver had failed, transitioning the event from a controlled flight path into an uncontrolled structural failure sequence. The forest canopy defined the physical survival of the central structure. The treetops became a progressive deceleration medium, stripping forward velocity without a single point ground impact. As the wings and engines tore through upper branches, drag bled off kinetic energy, disrupted lift, and left the aircraft suspended high above the forest floor before it dropped down and backward into the lower branches. That secondary fall imposed loads unlike the initial forward strike. The airframe was built for longitudinal flight stresses and positive aerodynamic loads, not for a backward drop through solid obstacles. The twin tail booms struck the heavy lower timber first. The leverage from the tail surfaces snapping against unyielding trees tore both duralumin booms away from the main wing center section. At the same time, deceleration forces reached the forward mass, tearing both Argus engines away and sending them separately into the debris field below. Stripped of its heavy engines and long tail booms, the remaining central structure continued its descent. The rapid loss of those outboard masses isolated the crew nacelle from the most destructive inertial forces. The central tub crashed through the final layers of branches and came to rest completely inverted. The extreme deceleration and fragmentation dictated the immediate survival parameters. 2 crewmen died from the combat and crash sequence, one reported killed in the impact and the other later dying from his wounds. The pilot survived and subsequently evaded capture. The inverted nacelle remained suspended in tangled undergrowth as a single intact unit, separated from the major aerodynamic surfaces and kept off the damp soil. The specific crash sequence left a readable local footprint. The separated engines, booms, and inverted nacelle allowed investigators to read the failure sequence from their surface positions before any metal was moved. Forensic verification began with the surface evidence visible before any metal was shifted. The investigators had to link the debris field to a specific operational record without disturbing fragile resting states. On the separated tail sections, the ground team located and carefully documented the tactical code Victor 7+1 Hotel. Alongside the tactical lettering, the surveyors found a distinct unit insignia, a white stork emblem still visible on the exterior duralumin skin. The dense forest canopy had helped preserve the paint by blocking direct ultraviolet light and slowing bleaching. Together, the code and insignia confirmed the wreckage identity without excavation or access to internal serial data plates. Proving the identity was only the first procedural step in assessing the site. The engineering team then had to map the precise spatial distribution of the airframe. Interpreting this layout required a careful understanding of the original manufacturing geometry. The FW-189 used a distinctive twin boom design, and its booms were designed to be interchangeable to simplify replacement and reduce spare parts demands in the field. This did not make the entire aircraft a quick-release shell, but it did mean that some major loads were concentrated through defined attachment structures. This design helped explain the post-crash debris field. When the extreme leverage of the accident exceeded the structural limits of the metal, the airframe failed around those vulnerable attachment zones. The resulting scatter pattern was not simply a random shattering of aluminum. It reflected the way external loads tore apart a machine built from distinct, serviceable assemblies. The surveyors systematically cataloged these separated assemblies. They mapped the twin tail booms resting entirely detached from the wing roots. Because the separation occurred around major attachment structures, the booms remained largely cohesive. The connecting metal was bent and the mounting areas were damaged, but the internal semi-monocoque frames still held much of their shape. The evaluation continued to the forward sections of the debris field. The surveyors inspected the sheared engine mounts and mapped the precise location of the heavy power plants. The engines had separated cleanly at the firewall bulkheads, which served as another set of primary modular attachment points. The central crew tub required the most careful forensic evaluation of the entire site. As the core of the original modular design, it had held all the primary load-bearing attachment points. The ground team mapped its inverted orientation and confirmed that the localized failure of the outboard joints had successfully isolated the tub from total destruction. The central structure was battered, but its boundaries were intact. By treating the site as a strict forensic grid, the engineering team established a complete physical inventory and the handling logic for each major unit. They now understood what lay in the timber. The unresolved problem was how to move it. In 1992, the recovery team faced a geographic barrier that turned ordinary salvage logistics into a dead end. The Lukey Forest presented a dense, unimproved timber canopy, and the wreck itself could not be treated like a normal roadside recovery. To extract multi-ton aircraft structures over land, recovery crews would normally use heavy transport trucks, tracked flatbeds, and mobile hydraulic cranes. In the Karelian forest, tightly spaced trees, uneven ground, and deep undergrowth, meant that any wheeled or tracked approach would require bulldozing a massive corridor through heavy timber, an approach incompatible with the wreck's fragile condition. Clearing such a path would directly threaten the historic metal. Felling massive trees near the unprotected duralumin carried an unacceptable risk of secondary impact, and vibrations from heavy earth-moving machinery on the soft forest floor could shift or collapse the inverted central nacelle. Ground-based recovery methods were therefore prohibited at the wreck site. That restriction forced a total recalculation of the extraction sequence. The site had to be treated not as a flat terrestrial grid, but as the bottom of a vertical well, with the stable lifting point placed above the forest canopy. The team began preparing the local area for a completely different mode of transport. Workers had to create enough safe access around the major components for inspection and rigging, while minimizing disturbance to the forest structure that still supported the wreck. This careful preparation allowed recovery crews to work around the separated engines, the detached booms, and the central tub. Because they could not slide a rigid flatbed underneath the wreckage to support it, the team had to identify surviving structural areas capable of carrying load without crushing the fragile glazed sections. Each subassembly had to be treated as an unstable historical object before it could be suspended by cables. The aerial platform had to hoist the bulky central section without dragging fragile metal against surrounding trunks. Once the wreck became a suspended load, pendulum effects became the central risk. The pilot had to hold a precise hover and keep the cable drop plumb to limit lateral swing. A standard utility aircraft lacked the lifting capacity and stability required for the heavier, aerodynamically awkward subassemblies. The operation demanded a dedicated heavy lift machine. The logistical effort shifted entirely away from securing trucks to arranging specialized aviation assets capable of performing precision sling load operations deep inside remote areas. Planners established a staging area miles from the wreck, at the first point where conventional trucks could operate on stable ground. The task narrowed to transferring the historical metal from the restricted forest floor to that receiving point without inducing further damage. The next risk was not access, but breakaway under load. The central nacelle of the FW-189 rested upside down, supported by branches and undergrowth. In that orientation, the original factory lift points were inaccessible or misaligned for a standard hoist, so the riggers had to establish a new artificial center of gravity. The vertical hoist geometry demanded strict snag hazard control. If the rigging lines were offset from the true center of mass, the central tub could tilt the moment the helicopter applied lifting tension. A sudden tilt would swing the jagged, sheared wing roots toward the rigid trunks of the surrounding trees. Under lifting load, a timber strike could tear the remaining metal apart. The rigging, therefore, had to be arranged under specialist supervision, spreading the load across the strongest surviving structure and keeping pressure away from the fragile, glazed framing. Before the lift could commence, the team had to manage rotor wash. Holding a heavy lift helicopter above the treetops required massive engine power, and the resulting downwash could blow loose debris across the forest floor or shift the nacelle before it was fully secured. Ground crews tied down loose metallic fragments and withdrew to a safe perimeter as the aircraft moved into position. The helicopter dropped a long steel lifting cable down through the narrow clearing in the canopy. Ground riggers connected it to the central lifting ring joining the soft slings, and the pilot began a slow, controlled pull to remove slack from the line. The breakaway sequence required constant monitoring. As the cable tension increased, the airframe slowly detached from the vegetation cradle that had held it for decades. The ground team watched closely for any trapped roots or tangled undergrowth that might act as an anchor. If the ground held the wreckage down while the helicopter pulled upward, the opposing forces would rip the airframe in half. The riggers confirmed the load was completely free before signaling the pilot to increase altitude. The hoist proceeded at a deliberate pace. With the load hidden beneath the canopy for much of the lift, the helicopter crew depended on ground direction and continuous communication until the inverted nacelle rose through the narrowest available path and cleared the upper branches. Once above the canopy, the pilot transitioned from stationary hover to forward flight, carrying the suspended load toward the designated staging area miles away. The recovery team then repeated this exact vertical extraction process for the separated tail booms and the sheared heavy engines. Because these outboard components were lighter and more compact, they required simpler rigging configurations but demanded the same strict adherence to vertical hoist geometry. By the end of the lift sequence, the central nacelle, detached booms, engines, and other recoverable components had been transferred to the staging area and placed onto transport. The physical extraction was complete, but leaving the canopy created a new conservation threat. The transition from a cold, static state into a less controlled environment initiated a conservation countdown. Once the wreckage was deposited at the staging area, open air, fluctuating temperatures, and variable humidity risked accelerating corrosion, especially where moisture and contaminants remained trapped in joints and crevices. Moving the metal now required swift logistical execution before avoidable material loss occurred. The components were loaded onto heavy transport trucks for the first leg of their journey out of Russia. The massive central crew nacelle, the severed tail booms, and the sheared engines were securely strapped to flatbed trailers. The convoy moved from the remote staging ground to a major commercial port facility. The entire physical inventory was then transferred to a cargo vessel for sea transport. The destination was Hull in the United Kingdom. This maritime journey exposed the airframe to a new set of environmental hazards, specifically the introduction of salt air and maritime humidity, requiring heavy protective tarping to isolate the metal. Upon arrival in the United Kingdom, the wreckage was moved into a specialized aviation facility where the operational objective shifted from physical extraction to forensic conservation. The engineering team established a controlled indoor baseline. The components were unpacked, documented, stabilized, and placed under monitoring to reduce the active corrosion risk that had increased once the airframe left the Russian forest. The engineers faced a distinct material limit. The aircraft was constructed largely from thin, gauge aluminum alloys, and harsh abrasives or aggressive chemical treatment could strip away the very metal they were trying to save. It could also damage surviving historical markings that helped prove the exact identity of the machine. Instead, technicians used controlled, low-impact cleaning and surface stabilization methods appropriate to each subassembly, from damaged engine firewalls to fragile plexiglass framing. The separated components were brought indoors, away from environmental weather loads and the worst chemical threats. The project later passed through major heritage ownership, including Paul Allen's Flying Heritage Collection, and by 2021 it was described publicly as an advanced restoration project available for sale. The operation proved that disciplined recovery geometry and environmental control could prevent total erasure. Yet the physical rescue left a final structural paradox. Can nearly 5 decades of forest exposure ever be reversed into a genuinely airworthy restoration?